Hey, it's Randy. Today we're going to look at some situations that involve exponential growth and decay, and then we will convert those situations into functions like the one you see here. Let's go. All right, first one. A bunny population in a field grows by 35% every 1.13 months. Let's remember, what's another way to say grows by 35%? Instead of saying grows by 35%, we could also say that the population increases by a factor of 1.35. And this growth by 35%, they tell us, happens every 1.13 months. Now, the initial population before observation began was 65 bunnies. So we started with 65 bunnies. And now we need to write an equation that models the bunny population that we're calling B of t as a function of time t in months. Okay, where do we start? So here's like the template function that we'll be using as we try to model these situations. So we have all of this is equal to B of t in this case. So let's start with A. What does A represent? Well, that is the initial quantity, which we are told is 65 bunnies. That's when time is at 0, when we have not yet started observing the change in bunny population. So now we have B of t equals 65 times what? What is B? Well, for our purposes, B represents the factor by which the quantity is 65, right? The initial quantity is multiplied over constant time intervals. Now, we've seen this concept before, and we call that the common ratio. Now, don't get freaked out by all those words, because B we just get from this rate of growth or decay. In this case, it's a growth of 35% every 1.13 months. But we need to describe it as a factor. So as I mentioned before, 35% growth is growth by a factor of 1.35. Now, before we continue, just for good measure, let's talk about what would be the value of B if instead of a growth, we had a decrease by 35%. We'll just write it right down here, and then we'll erase it in a minute. So if we had a decrease of 35%, that would be a decrease by a factor of 0.65. Why 0.65? It's because 1 minus 0.35 gives us the 0.65. But in this problem, it's a growth, so our B is positive 1.35. All right, now let's look at f of t. It is an expression in terms of t that determines those intervals. So for our purposes in this lesson, f of t is just going to be t over the given time interval. In this case, we have 1.13 months. And pretty soon here, you'll see why this right here, the t over the time interval, makes total logical sense. So in this case, the time interval, the denominator, is going to be 1.13. So looking at the original question, they said, write an equation that models the bunny population B of t as a function of time t in months. And that's exactly what we have just done. So the function that is the answer to this question is right here. B of t equals 65 times 1.35 to the power of t over 1.13. So hypothetically, instead of 1.13 months, if we had a time interval of, say, 5 years, instead of 1.13, we would put a 5 in this denominator. If the time frame was, let's say, 8 days, instead of 1.13, this denominator would be 8. Now, before we do the next example, let's just talk about why it makes sense for f of t to equal t over the given time interval really quick. We know that f of t is equal to this entire fraction, t over 1.13. So first of all, what if we plug in a 0 for t? What will that give us for the value of B of t, or the population of bunnies? Well, if we have 0 in the numerator right here, that makes the entire exponent 0. And 1.35 to the 0 is 1. So 65 times 1, or 65. Okay, so that makes sense because we know that when time was 0, the bunny population was in fact 65. Now what happens if we plug in 1.13 months instead of 0 for t? Well, that will make our entire exponent 1, right? 1.13 divided by 1.13 is 1, which makes this entire exponential part of the expression just 1.35 to the power of 1, or 1.35. Just like that. And if we do 65 times 1.35, we should get 35% more than 65, right? Because we're just multiplying it by a factor of 1.35. So after 1.13 months, because t was 1.13 in this case, we would get almost 88 bunnies. And then if you plug in double our original time interval of 1.13 months, we should get yet another increase of 35% in the bunny population, which is in fact the case, and so on and so forth. So the point is that when we use this function to try to predict exactly the situation they described, we see that we do in fact get the values that we should. We get the exact growth rate that we expect when we have t over 1.13 as that exponent. All right, let's do another example, but this time we will have exponential decay instead of exponential growth. Carbon-14 loses half of its mass every 5,730 years. The initial mass of a given carbon-14 sample was 88 grams. Write an equation that models the remaining amount of carbon-14, that is C of t, as a function of time t in years. This time we have years instead of months. So as usual, I encourage you to pause it and try to set up this function yourself. All right, let's do it together. So what is our initial quantity of, in this case, carbon-14? We know that that will correspond to A, and it is 88 grams. So A will be 88, and then what about B? What is the common ratio? What part of the question do we need to look at to find that out? Well, right here it says that carbon-14 loses half. What is another way to say loses half? Well, we could say that its mass gets cut in half every 5,730 years, or we could also say that its mass decreases by 0.5. That is a factor of 0.5. So 1 minus 0.5 is also 0.5, so this 0.5 corresponds to our B, our common ratio. So let's set up what we have so far, and then we will put our f of t. All right, c of t equals 88 times 0.5 to the power of what? Well, as we discussed, f of t, in our case, is going to be t divided by the time interval that we are given. The time interval is 5,730 years. And there it is. We now have a function that models the remaining amount of carbon-14, c of t, as a function of time, t in years. Now, if you get stuck as you're trying to answer questions, just refer back to this key. And that is how you construct exponential models. See you next time. Hey.